Now that the prerequisite part, Chapter 1, is behind us, we're going to move on to Chapter 2, Limits and Derivatives. This is where the real course materials for Calculus 1 begins. Here, our textbook author decided to put together the limit concept and the derivative concept in the same chapter. In my supplementary notebooks, I decided to separate them. Actually, I decided to separate them into 3 different and independent topics: limits, continuity, and then derivatives. The first of the 3 is a limit, and we're going to follow this order. It's a little bit different from our textbook's order. First, we're going to talk about the limit and continuity with graphs. Because we can see the behavior of the function with explicitly given graphs, we can understand the idea behind limit and continuity a little bit better. At least that's what I hope. And then we're going to move on to the limit rules, which are the basic building blocks for limit computation. And then, of course, we'll do a lot of limit computations. Let's go. Let's begin with a couple of motivational examples. Here's one. Let's suppose a graph of y equals f of x is given as follows here. I hope everybody can see that there are 2 very interesting points, or singular points, where x equals to -4 and x equals to 3. And of course, in all other points, we have generic behavior. Here, what I would like to focus upon is the distinction between so-called point properties and the local properties. What do I mean by point properties? The properties that is related to a single point and nothing else. Function values, for example. Here, what is f of -4? All we have to look at is a single point right here. When x equals to -4, the y-coordinate value given by this graph is 3. What about f of 3? Again, that's answered by the same point. The single point. Not the same, We see 2 different points, of course, but a single point. X equals to 3, then the part of the graph is the single point. So f of 3 is y-coordinate value of this second point. That's going to be 1. However, if you look at this x equals to -4, you will notice overwhelming majority of the points, other than this lone exception, are concentrated around here. When x is not equal to -4 but pretty close to -4, the closer the better, then y-coordinate will approach, well, this value, y equals to 1, either from the right hand side or the left hand side. That kind of thing is called the local properties, and limit, derivatives, and, well, all kind of things we learn in calculus are local properties. That's kind of quantum leap from pre-calculus to calculus, from point property to local property. Here's a basic notation. F of -4 is equal to 3. We discussed that. Next one, we talk about the local property. We read it as follows. Limit as x is approaching to -4, f of x is equal to 1. So x is getting closer and closer to -4, either from the right hand side or left hand side. Y-coordinate value on the graph is following and getting closer and closer and closer to 1. And that's what we are looking at, whether I move from the left hand side or right hand side. When x equals to 3, or when x is pretty close to 3, we have these behaviors. When x is approaching to 3 from the left hand side, that is, x is a little bit less than 3, which is represented as 3 minus, negative side, then I'm following this part of the graph, and then y-coordinate value is getting closer and closer and closer to 2. The other one, 3 plus, represents when x is approaching to 3, but a little bit greater than 3. Plus means greater than 0, isn't it? So from the right hand side, I have to follow this graph, and what do you get? Y is getting closer and closer and closer to -1. This one is called the left hand side limit. That one is called the right hand side limit. And please note that in this case, the left hand side limit and right hand side limit are different. In this case, we say the limit is undefined, or limit does not exist. Compared with the previous problem where the left hand side and right hand side limit are the same, right hand side, left hand side both approach to +1. In this case, limit exists and the limit value is 1. That's not the case for x equal to 3. What if x is neither -4 nor 3? For example, how about x equal to -2? It could be any other point, but I just decided to select this one. Here, the function value, the y-coordinate value, or the limit value, getting closer and closer and closer, to left-hand side, right-hand side, they're all the same. Just like this, if they're all the same, we say the function is continuous there. So in this case, we can see that function f of x is continuous at x equal to -2. Actually, it is continuous everywhere except for -4 and 3. Here is another motivational example. This one deals with some asymptotes. We can consider same kind of local behavior when x is approaching to a certain number. I hope everybody can see that there are two very interesting x values, -2 and +1. And to which y-coordinate values do the graph get closer and closer and closer to? Because of the asymptotic behavior, looks like the graph is blowing up to +infinity or -infinity, depending upon which direction am I getting closer and closer and closer to -2. In this case, whether I approach from left-hand side or right-hand side, the graph both blow up to infinity, +infinity, at x equals to 1. And those should be reflected by appropriate signs of infinities. What if x approaches infinity instead of y? That's going to be reflected by horizontal asymptotes here. I'm moving to the right hand side or the left hand side. We're going to come back to these in a moment. Let's talk about some formal notations first. Alright, let's review what we just talked about using those motivation examples. The limit concept, or limit notations, more precisely speaking, can be expressed in this fashion. We read function f of x converges to L as x approaches to C, just like the examples, the graphs we saw before. And we say limit x is approaching to C, f of x is equal to L. And when left-hand side limit and right-hand side limit are two different values, just like the breaking behavior we saw before, then we use this notation: C minus for negative side, left-hand side, C plus for right-hand side. If those two are the same, then we say the limit exists, and then we use the limit concept without those pluses and minuses. If those values are all the same, limit exists, and then that's equal to the function value, or equivalently speaking, if the left-hand side limit and right-hand side limit both exist and they're all the same as the function values, then we say the function is continuous at x equal to C, and that was the case for overwhelming majority of the points on these examples here. This example, this notebook, which is posted on Blackboard, is filled with redundancies. Of course, that's my intention. We have the same example that we saw before, but notation this time are all a little bit more formal than the one we saw before. We discussed this very same example, so doing these problems according to these formal notation is left to the students. Let's move on to asymptotes. Well, we're talking about the same picture again, and again, this is my intention. There is redundancy here. We're talking about the same example we saw before, and what do you mean by vertical asymptote? That means y-coordinate is blowing up to positive infinity or negative infinity, depending upon the direction. What do you mean by horizontal asymptote? That's when x is approaching this infinity or negative infinity. According to that observation, you can answer these questions. How about this one? F of negative 2, of course that's undefined, no point here. X is approaching the negative 2 from the left-hand side, negative side. That's a left-hand side limit. Now what is this left-hand side limit? If I follow the graph from the left-hand side, y-coordinate is blowing up to positive infinity. How about the right-hand side limit here? Negative 2 plus. We have to follow the graph from the right-hand side. So follow the graph from the right-hand side. Looks like this is going up to pit, negative infinity. We're talking about two different infinities. Consequently, the limit is undefined. Positive infinity, negative infinity, those are reflected by the splitting. How about problem B here? We are looking at problem when x equals to 1. In that case, whether I follow left-hand side or right-hand side, function values just blow up to infinities. So limit at 1, x approaching to 1 from the left-hand side or right-hand side are the same, both positive infinity. Consequently, the limit exists and the limit is infinity. What was the difference between one and the other? Graphically speaking, we had splitting in this vertical asymptote. We had dragging in the second vertical asymptote. Now let's answer the questions about horizontal asymptotes. X is approaching to negative infinity. That means we have to go to the left-hand side. That y-coordinate is getting closer and closer and closer to negative 1. When x is approaching to positive infinity, we have to go to the right-hand side. And that y-coordinate is getting closer and closer and closer to 0. Clear observation. In summary, we went through the formal limit notations and then how to associate the limit notations with given graphs, how to deal with expunged points, how to deal with breaking up, how to deal with asymptotes, asymptotes, both horizontal and vertical. There's one additional topic here. Let us summarize commonly encountered infinities. There are some. And then what about 1 over 0 type? Well, that's going to be infinity, yes, but it'll depend heavily upon the sign, positive or negative, and that's reflected by this graph. When it's approaching the 0, a little bit positive side and positive infinity, left-hand side, negative infinity. And going to positive infinity or negative infinity, 1 over infinity is going to go to plus or minus 0. So those are reflected by this kind of graphs. Another kind of graphs that show up a lot will be exponential and logarithmic functions. Here, blue is exponential, red is logarithmic, and e to the positive infinity is positive infinity, yes, blowing up to infinity. E to the negative infinity is a little bit more interesting. That's going to be 0 because if you follow this graph to the left-hand side, we have horizontal asymptote. Logarithmic function, we have vertical asymptote, but when x is approaching 0 from the positive side, so that's going to be negative infinity. All these are one-sided limits. And another examples that appear relatively often is coming from tangent function. Tangent function, we have splitting when x is equal to pi over 2 or negative pi over 2 or 3 pi over 2 and so on because this is periodic, or arctangent function where we have, well, horizontal asymptotes. The limit notations related to these horizontal and vertical asymptotes are summarized like these.